Hello, this is a video about discrete probability distributions, and I'm going to try and show you everything you need to know using 4 different examples. Right, let's think about the easy one, tossing coins. If you toss one coin, the number of heads you can get is 0 and 1. Right, you can get a tail, which is 0 heads or 1 head. So we can put that in a table here. X is the number of heads you get, and there's the probabilities of each, half and half. Okay, if you got 2 coins, this is over here, you can see the possible outcomes you could get. So you got no heads, 1 head, or 2 heads, which we keep over here. And then there's the various probabilities of those things. Okay, and if you toss 3 coins, you could get all these possibilities over here on the right. And so that's no heads, 1 head, 2 heads, or 3 heads. And probability of no heads is 1/8, then 3/8 for 1 head, 3/8 for 2 heads, and 1/8 for 3 heads. And so this table we've just drawn is your discrete probability distribution. It tells you what are the possible outcomes, and that's in the first row, and the second row, the probability of each of those outcomes. So the probability is distributed among the different discrete outcomes. Notice you can't get half a head or 0.378 heads. It's discrete number of heads there. Right. What we can then do is with that information, we can make not just a table, but a graph. And that graph displays how the probabilities are distributed. And you'll see that you've got your 0.375, your 3/8 in the middle here, and your 1/8 on either side. You'll also notice that the probabilities in the second row have to add up to 1. Okay. What is really useful here also is to think about what's going to happen if I repeat the experiment lots and lots of times. So if I were to do the same thing, toss 3 coins, but do it 500 times, how many times out of those 500 would we see 1 head? Well, if we did it 1 time, potentially 0.375 of a time, you'd get 1 head. So you just times the number of times you do it by the probability of that outcome, and it's 187.5 times. And it's okay to say 0.5 because it's an average, it's an expected value. That's why it's called E of x, because it's expected value of the discrete random variable. How about more than 1 head? Well, what's more than 1? That's 2 and 3. So we've got to add up the probability of 2 and the probability of 3 and times it by 500. Okay, here's a new example that we don't know what actually the scenario is, what's going on, but it's distributed like this, 0, 1, 2, 3, and the probability of each. One probability is missing. How do I work it out? Well, like I said about a minute ago, all those probabilities have to add up to 1, so we just do 1 minus the rest of them, and we get 0.3. What does that x equals 0.3 represent? It's the probability that you'd have 2 successes if you conducted 3 trials. Okay, that's what it just means. You have a total of 3 trials. This is 3 successes, 2 successes, 1 successes, no successes. Okay, new example. We've got a spinner. It's got different fruits on it, and we're going to spin it 3 times. And how many times is it going to land on pineapple? So what are the chances of getting no pineapples, 1 pineapple, 2 pineapples, or 3 pineapples when we spin it 3 times? Okay. On my little graph here, on my little table, sorry, I've used P for pineapple and N for not pineapple. Okay. So how can I get no pineapples? By getting not, and not. So there's only one way for that to happen, and there's 6 results and 5 of them not pineapples, so 5/6 is the probability of getting not pineapples. We do it 3 times, so you cube that. Getting 1 pineapple, there's 3 different ways that can happen, and all 3 of them have the same probability because they're independent. So it's 5/6 for not pineapple, 5/6 for not pineapple, and 1/6 for pineapple. Again, there's 3 different ways to do it. And similarly, for 2 pineapples, there are 3 different ways it can happen. And the probability of getting that is 1 not pineapple and 2 pineapples. So it's 5/6 times 1/6 times 1/6. Getting 3 pineapples is 1/6 times 1/6 times 1/6. And there's our 4 different scenarios. And if you add them all up together, which you should do, you will notice you get 216 over 216, which is 1. Has to be that way, otherwise you've made a mistake somewhere. You can also take that and draw it as a graph, which shows you that very small chance of getting 3 pineapples in a row, big chance of getting no pineapples at all. Okay. So what are the chances? That's what we just worked out previously. So we've got that table there. What's the long-term average number of pineapples? Well, this is something called the expected value of x. And we expect 0 to happen that proportion of the time, 1 to happen this proportion of the time, and 2 to happen this proportion of the time, and 3 to happen this proportion. So you multiply your x by the probability of x and add them all together, and you get 0.491. And this is actually cool when you draw it as a graph, because you can see the mean would be about there on my graph. It's not the best graph, and because it's discrete, it doesn't quite work, but you can kind of use it, the idea. 0.491 is there, which means the area on this side of that is about the same as the area over this side. So it kind of makes sense that it's the mean. Okay, so that's a very important formula to remember. It's the expected value is the sum of x times the probability of x. Okay, new example. My football game plays 4 matches. Probably they win any game is 0.4. Let's fill in a probability distribution table. So x is the number of wins, so I can win 0, 1, 2, 3, or 4 of the games I play. Okay. To lose all 4 is 0.6 to the power 4. To win all 4 is 0.4 to the power 4. The other ones, like here I lose 3 and win 1, and there's 4 ways that can happen. If I win 2 and lose 2, there's 6 ways that can happen. If I win 1 and lose 1 and win 3, there are 4 ways for that to happen. And so that gives me my outcomes. Okay, and I can graph that as well. Got to know probabilities have to add up to 1. You can also do it if you're not familiar with this formula. You can use on your calculator. You can use the binomial PDF function. That will give you the values that you're looking for there. I have another video that explains this formula in a bit more detail. I'll put a link to below. Basically, it's a number of times something can happen. The probability of success to the power of number of successes, and the probability of failure to the power of number of failures. One more example. You've got 5 goldfish. Probability that a goldfish will live for a year is 0.8. What's the probability of a fish being alive in a year? Well, we've got 5 goldfish. Probability that no goldfish are alive is 0.0032. The probability that 5 are alive are 0.32768. Okay, how I found all these numbers was on my calculator using the binomial PDF function. If you don't know how to do that, you can look it up somewhere else. We'll run out of time in this video, so I'll post the link somewhere. But note that the probabilities have to add up to 1, and it looks like that when you graph it. Okay, what's the probability that at least 3 of your fish will be alive? So at least 3 is 3 or 4 or 5. So you add those 3 probabilities together. So it's a 94% chance I've got 3 fish next year. You can do that with binomial CDF or binomial PDF and add them all together. But that's another lesson. Now, there's the probabilities we've already got. Now, if you had a lot of people who had 5 goldfish, what would be the expected number of goldfish you'd expect to be alive after 1 year if you all started with 5? Well, if we do the x times probability of x, add it all together, we will get, in this case, 4, which makes sense when you look at the graph, how the bars on the left of 4 and the bars on the right of 4, if you add up all those areas, they'll be about the same. Okay, so that's my 4 examples, and I hope you've got some good ideas of how to answer these types of questions and ideas of where the formulas come from and how to use them. All right, good luck.